Okay, good afternoon, everybody, and welcome to Compass. It is my pleasure to introduce Dr. Sharan Majumdar, who's one of the atmospheric science faculty here at Rasmus. This is part of our special series of the faculty at Rosenstiel to introduce themselves to everyone. I believe this is our first special faculty seminar of the spring semester, so welcome back from the holidays. And as Sharan told me just a few minutes ago, his talk today will be about 30 papers in 30 minutes. So with that, I will turn the floor over to Sharan.
All right. Thank you very much, Aidan, for the gracious introduction and for Roland for expertly organizing all of these seminars and a video and a Zoom and everything, taking care of all of us who are more technically challenged than he is. So yeah, it's a real pleasure to sort of kick off this semester that Amy Clement will be following this time next week, so everyone should roll up to that as well. So yeah, this talk is kind of split into two, maybe three parts. The first of it is a little bit of an academic life story and some of the rather interesting twists and turns. Some of my early research, the way before sort of anyone here was in Miami, maybe even before some of you were born. And then much of it, as Aidan referred to, 30 papers and 30 slides, is kind of this very general overview of a lot of research that former and current students are doing, and really just with one key question that each of them were addressing. So it's been an experiment. I hope that it's sort of more cohesive than it sounds, so let's jump right into it. So it's really first where I came from. So by my accent you can tell I'm from the UK. I grew up in an old Roman town called St Albans in the UK, which is really quite a nice place. And then I went to Cambridge University, where I studied mathematics, and I almost didn't get in. I didn't have the right grades really to get in. I messed up on a couple of my exams. But yeah, this guy, John Hudson, he let me in anyway. He saw something, he said, like just when he interviewed me. Yeah, he was kind of a main mentor through my undergraduate 3 years in Cambridge. He was a theoretical seismologist and now retired. And for the first time in 30 years, and we see each other very frequently, but for the first time in 30 years, we're actually talking about tropical cyclones, because he and his wife are going to Mauritius. It was supposed to be yesterday, but there's a cyclone that has just formed that's making landfall right now. And so they're literally taking off just 20 minutes ago, hopefully. Yeah, he did a lot in just sort of helping normalize me as I was a rather unstable undergrad student, and just sort of trying to figure out how everything worked. And he was just always there, just to sort of help guide me through the whole craziness of being an undergraduate there. I like Cambridge, and so I was pretty happy to stay on. There's a few characters here. And so the person in the middle is the late David Crichton. This is a life-size portrait of him that hangs in my old college. That he was quite a legend. And I took a fluid dynamics course from him, and then our course evaluations are pretty much optional in the UK. And I had a couple of pints and I wrote out the course evaluations. Of course, when you have a couple of pints, things get a bit extreme either way. So I wrote some not very nice reviews about some of the instructors, and I wrote a really glowing review about him. And I gave it to John Hudson the day afterwards and said, well, here, you can have these for a laugh, and didn't think it would go anywhere. But John actually must have told David, because David came to see me, and I thought, oh no, what did I say? And he didn't know me at all. I was just a kid in the class, a pretty big class. And he said, oh, thank you for those comments. And so sort of sheepishly, we struck up a bit of a friendship right there. So yeah, he was pretty keen for me to stay on to do a PhD. And his area is aeroacoustics. He was the equivalent of a dean at that time, and not really spending much time doing hands-on research. So he assigned one of his recent graduates, Nigel Peake, to be my primary advisor. Nigel had just joined the faculty, so I was his first student. And so what my PhD dissertation was really driven by noise requirements by airports. So, of course, as aircraft take off, especially also when they land, it annoys people who are trying to get to sleep near airports. So, because of that, the engine companies, so Rolls-Royce and General Electric and others, they needed to make quieter engines, and so Rolls-Royce funded my research to try and do that. I really I wouldn't say I developed, but I sort of expanded on a theoretical noise prediction scheme. And essentially, we had sort of models of aircraft engines. We essentially linearized the Navier-Stokes equations and looked for all these sort of complex variable type solutions to the tonal noise that is shed by aircraft engines in two different conditions, one in flight and then the other when it's in testing. And of course, the atmosphere is very different and much more stationary relative to the engine when the engine's being tested. So that was a lot of fun, but it was also something that I didn't really want to do for the rest of my career. I enjoyed it a lot. It was very kind of engineering. I was a little bit worried that all my work would just kind of sit there and gather dust, which actually it did until recently. And there are now stricter noise regulations, and so the aerospace companies are saying, oh golly, we've got to make our engines even quieter. And so now my paper from 1998 now starts to get cited again quite a bit, so that's nice. So yeah, in the middle of all of that, I also, through another professor at Cambridge, ended up on an internship going to Australia with three of my friends. And I worked with the Australian equivalent of NOAA there, and that was my first exposure to ocean and atmospheric science. That, unlike probably most of the people in this room, I had no interest in meteorology at all, even after graduating from my undergrad. That I thought meteorology was completely boring, but I wanted to go to Australia. I actually lived in Australia for a year when I was 4, and I remembered bits of it too. And there were people who really sort of helped take care of my parents a bit, and then me too. And so I wanted to see them. So I went to Australia, worked to the equivalent of NOAA a couple of summers, including the summer of 1993. And here's a picture of a pretty bland and pretty empty station. And it was one day, and it was a very weird day at work because there were some sort of political issues at work. And I thought at 5:58, well, let's see if I can catch a 6 o'clock train. I don't really want to stay at work anymore. And so I sprinted to the station, just made it in front of the train here, popped up on the station. It's just one other person standing at the station. And that person had been giving a lecture earlier that day on clouds in a glass of beer. And so it's a topic, and it's a pretty exciting lecture, so I remembered it. And I'd asked a question, and so he remembered who I was. And so, I went in, I didn't have my headphones on, I didn't ignore him. I thought, oh yeah, it's okay, we sit and chat. He's like, yeah, sure, fine. And it's actually a message that he gave a bit later when he introduced me in a seminar, that it's really useful to, whenever you get opportunities to chat with people, to just do so, and you never know where it might lead. So the person here, which many people here have heard about, so I talk about him all the time, is Craig Boren. So he's now a retired professor at Penn State, then he was pretty active. And so, that's his old book in the middle there from 1987. This picture on the left is from 5 days ago. So I was visiting them for a long weekend, and we had about 3 to 4 inches of snow, so we went on a little hike up in the snow, so that was good fun. And then this was just from a year and a bit ago. They live up in the mountain just behind the photo of us, just right there. We actually wrote these 4 to 5 page letters, real letters, and posted them by snail mail in the mid-90s when I went back to Cambridge and he went back to Penn State. He was just giving a lecture tour around Australia when I bumped into him. So we were both strangers in a strange land. So what that then led to was a couple of things. One is the Atmospheric Thermodynamics textbook, which he wrote with Bruce Albrecht, who is a very key player in all of us being here. because Bruce was a professor at Penn State, then he moved to the University of Miami, UM recruited him, and then Bruce essentially hired us at atmospheric science faculty, and so there's a little Miami connection right there too. But anyway, yeah, through meeting Craig, I ended up going to Penn State for a conference in aeroacoustics to present my PhD work. And I really wanted to go to see Craig, and then he said that, well, you can come and see my department. Oh, my dad went to Penn State as well, so that was actually also a bigger reason for wanting to go. So then I ended up being recruited more or less on the spot in the department of meteorology there by another Craig. And just to make it confusing, this is an Australian Craig, whereas the other one's an American Craig who I met in Australia. This is an Australian Craig who I worked with in the US, Craig Bishop. So he was a junior professor then, quite a character, quite exuberant, and was just starting to develop data assimilation techniques at the time. And so, yeah, he hired a few of us in our targeted observations and data assimilation group. Yeah, we had a really good time at Penn State. So I'll talk about some of that work in just a little bit. And then it was on to Miami, and that was also a bit of a chance occurrence. You're not quite as crazy as the train station situation. But in 2000, I really didn't know what I was going to do. And I was a bit down on things that David Crichton had just died, and he died sort of very young too. So I was pretty upset about that and just wasn't really sure, and partly didn't really care about what my short-term future was. But I had been to Miami before, and I'd worked a bit at the Hurricane Research Division across the street from here. And I also got to meet Bruce on that trip in 1998. One of my friends worked at United Distillers, who were owned by Guinness, and they put him up in this gigantic penthouse apartment in South Beach. And so he's like, well, you can stay as long as you like, I've got a spare room. So I ended up spending a month in Miami and getting to know people in Miami in 1998. And then that actually then really paid forward, because then there was a job ad that was put out for a lecturer position here, which I initially deleted and then forgot about it and went back to coding. And then I think a few hours later, I was like, wait a second, I should probably see the person who sent that message. So then he sent me the message again, and then I applied for the position here, and it was just a lecturer position. And so then I came here, but not really knowing what I'd be doing after that. It was just sort of a stopgap. Then they advertised a faculty position. They're really trying to build a faculty. And so they put a faculty announcement, and so I applied, and Dave Nolan applied for it as well. And so I thought, oh, well, okay, I've got no chance now. And somehow, and I'm not really sure how, and I'm too afraid to ask, they hired both of us. And so, yeah, Dave and I are here, and we'll talk a lot about our mutual work as well through this talk. My teaching in Miami is comprised 9 separate courses in total. Mostly undergrad, that we really needed to sort of meet all the AMS requirements. Amy was new at the time as well, and so we were all trying to teach quite a lot at that time to meet all the requirements and not having a really full faculty. And then also a few graduate classes. And the ones that are in blue are the 3 courses that I currently teach, and there are also 3 that I developed, and there are not really any textbooks in it, and so they're really great fun to teach. And as you'll see, they're just very much intersecting with research as well. I also really had a nice opportunity to sort of take a few leadership roles as well in the university. And I think a lot of that stemmed from David Crichton, even though I didn't know him that well. I was just a grad student. I also wear a tie, really in David's honor. I forgot about it actually until this morning. So, oh yeah, that's why I started wearing a tie. And it sort of as I started some of these roles, kind of following in Amy's footsteps a little bit with all of these positions. And those were just really great fun, because I got to interact with all the grad students in all the different departments, and knew them all by first name and everything. So that was a fun time in the 2010s. And I thought I'd get back to research, and then went on sabbatical at ECMWF. And then I got sort of voluntold by our recent provost, Jeff Dirk, that I need to start something called a Climate Resilience Academy. And I actually didn't know what climate resilience was, but I'm like, okay, fine. It's COVID, I'm sitting on a couch, what else am I going to do? So for a couple of years, that was fun, sort of building this big interdisciplinary initiative with sort of much of the university leadership and faculty. And it's especially good that we've got an awesome permanent director now too, Michael Berkowitz, and he'll come to Rosenstiel School a few times. He was one of the participants in the Climate Cafe along with Brian last week. Okay, so yeah, let's get into a little bit of science. So a lot of my work is really inspired by Ed Lorenz. And all of those in my predictability class know these by heart. And actually, I forget who actually did these plots that I'm showing. And so Ed Lorenz produced, of course, many seminal papers in the world of predictability. And there are three that are really my favorites here, and a lot of profound messages from those papers, from some very simple numerical experiments. So this shows the classic Lorenz attractor here. And there's a red line and a black line, and they're essentially two solutions of exactly the same three-dimensional ordinary differential equations, but with very, very tiny changes to their initial conditions. And so they look exactly the same in this solution. It's easier to see in the 2D plot here, right out to time 20 units. Then we start to get slightly different. And then by a few time units after that, they get very different, and the two states become indistinguishable from each other. And so a profound conclusion here was that even if you have a perfect model and infinitesimally small initial condition errors, you're going to lose your forecast skill after some time. Then in 1965, he had a 28 variable model, which was quite advanced back then. And he computed these measures of error growth, so I thought, well, this would be pretty cool for the class to try as well. I think, Aidan, this might be yours because it's got different colours for all the different sticks here.
You're kidding.
And so on the y-axis here is the error growth rate over successive 2-day periods. And so we see that the error growth rates are fairly flat through most of these periods, but then between 6 and 8 days, there's a very high error growth. And so this shows that depending on the flow regime, you can get very different error growth rates. So you can't really just generalize predictability overall here. And especially if there's some sort of regime change, like a frontal passage, for example, then you could get some pretty substantial error amplification, even in a short-range forecast. So flow regimes are very important when we want to think about predictability. And then finally, his 1969 paper really speaks about the scales of motion. And so this is just taken from that paper. On the x-axis gives the length scales from large length scales on the left to the very small, even turbulence length scales at the very right of this picture. And the curve shows the time at which errors would saturate on the different scales. And so he used a fairly simple model for this, and then provided, as he did, some pretty profound conclusions. So this is what really triggered what's known now as the butterfly effect, where small errors, initially small errors, can sort of grow across the scales and start to saturate the scales as time increases. So on convective scales, you get saturation perhaps about an hour, synoptic scales sort of order of days or so, and so forth. He actually used seagulls rather than butterflies here in this paper, but I think someone said, well, seagulls are boring, so change it to butterflies and you'll get a lot more attention.
Wasn't it the title of a talk somewhere? Did he give that talk? Does a butterfly in Brazil change?
About, yeah, the butterfly in Brazil changing.
Was that him or was that someone else?
That might have been Lorenz, I think. Yeah. I also put a picture of an elephant here too, and that's not random. That Lorenz did a numerical experiment on this, but it was kind of forgotten about a bit. That very small errors in the large scales are going to very quickly saturate the smaller scales as well, which is a very important point in practical predictability. And I think that's as important, if not more important, than the butterfly here. So on the topic of practical predictability, which is I guess where I sit in a little bit, there's a three-legged stool of observations which you want to use to most accurately represent the state of the atmosphere, and then you want to assimilate those observations through some combination of the observation data and their errors and some previous guess of the state of the atmosphere, or the ocean, or whatever state you want to make an analysis and prediction of. And then modelling, and I'll probably add a fourth leg of it, that's sort of probabilities as well, that we can't really do things deterministically, that we need to sort of understand uncertainty because our whole world is uncertain. So back to the Penn State days, which used a lot of these principles of Ed Lorenz. And we used this in a way that was just being developed right at that time with Craig Bishop and a few others, was his techniques for targeted observations. So what are they? We have this timeline here, and we want to improve a forecast at some future verification time, which is TV. And say we've got use of some aircraft or satellite observations at an earlier time, TA, and it could be of a situation such as a landfalling cyclone over California. So we've got to select our case, so forecasters do that. We've got to provide some sort of guidance as to where to deploy extra observations. And then we've got to decide on them. So the techniques that we developed, the ensemble transform-Kalman filter, that involves ensemble forecasts, it involves data assimilation, it involves the forward propagation of errors and accounting for different sets of observations. So that's a whole separate talk in itself. And so we used forecasts that initialized at this time. We had to make a decision at some future time. This is usually about a 24-hour window, and this is usually about a 24 to 36-hour window for deployment of aircraft. And then we want to improve forecasts of generally like 2 to 5 day forecasts. So this is a typical map of targeting guidance. Usually it was in baroclinic zones for this winter storm reconnaissance that we used to do. Actually, the code is still being used at NOAA, and I was pretty shocked by that. That Vijay Talapragada up at NCEP, he said that, we still use your code. I'm like, okay, we've got some interesting comments in there. And so we deploy the aircraft dropsons in the target areas, and that's important to then evaluate whether those observations had a meaningful influence on the forecast. So I got roped in by the World Meteorological Organization because there was a lot of debate across multiple agencies about the value of these targeted observations. And the general result was that the influence of the targeted observation in the forecast was generally pretty small. But think about it, you've got about 20 dropsons, and you've got literally about 100 million other observations, mostly from satellites. So it's a very small number of additional observations that we're adding into the network. Then also the scales may not be quite right, because we're targeting for synoptic scale events here, but then we can't really capture the full extent of these sensitive areas that may be across multiple scales. So I ended up sort of closing my career a bit in targeted observations with a review article in a bulletin of the American Meteorological Society that was really initially put together with this working group. Then they said, well, here, you go write it yourself and put your own opinions in there. And so this was a nice article to write, and I really liked the review process. It actually got rejected first time, and it improved it a ton because of that. And so one of the key goals here is, in the future, is optimize the use of the routine observational networks. That means satellite targeting, satellite thinning, for example. Embrace new observing platforms, such as targeting of unmanned aircraft, and then also look at prediction where you can actually target the right areas for, and so perhaps evolve more towards convective scale predictions. However, all our techniques have linear inferences, and they may not be quite so appropriate for convective scale prediction. Another one, I was really quite frustrated by this back around the mid-2010s, was that there are very few evaluations of these field campaigns. That people go out, they'd fly their aircraft, and then they'll all go home and they'll do something else. I have to say that NOAA's done a really good job since then. Like for the hurricane reconnaissance, like Jason Sippel and company do a lot of these data denial experiments with dropsondes. So I now have a lot more confidence than I did back then that people are really doing much better evaluations, and they're also putting some scientific understanding into why the observations are affecting forecasts the way that they are. And then the third one, which is only really taking off now, sort of nearly 10 years after I wrote this, is assessing the socioeconomic value of improving these forecasts. So that's important, for example, if you want to launch a new satellite for a particular purpose, then it's useful to know what their potential value is for society. So it's a bit of a cost-benefit analysis there. Okay, let's go to the next part, which really involves many people in this room, which is now the tropical cyclones. And with targeted observations, I sort of felt it ran its course a bit, and there wasn't a lot of really great science that was coming out of it. At least I tackled all the questions I really wanted to. So I was really interested in tackling a lot of predictability questions that are connected to the processes there. And so, of course, being in Miami, you really want to help build up expertise in tropical cyclones and recruit lots of awesome grad students, which of course we've done, and really look at these particular elements of tropical cyclones. And we've taken many different approaches here that much of it, as you'll see, uses operational models and ensemble forecasts. Much of it also uses reanalysis data, especially with the RA5 coming online the last sort of 6 or 7 years or so. The quality of that data set has allowed for a lot more interrogation of scientific questions related to predictability and processes. And then also a lot of Dave Nolan's idealized modeling framework to tackle some of these questions in a more controlled environment has been very valuable for this. Okay, pictures of research groups, and time to embarrass people here a bit. This was a lunch, it was a dinner with Dave's and my research group. So Dave, you're right at the back there, and I only label those in my research group. So when you give this talk, Dave, then you can label everybody else. So yeah, there are 18 of us here, a lot of alums and then current students, and Brian is a constant in all of these. And so we'll show the work by all those who worked in tropical meteorology here from them. So yeah, some of you know some of them, but they're really past students largely. And then just a few more as well, because Ting Chi wasn't in that other photo. She was having a baby at the time, so we have this photo as well with a few of the same faces again. And you'll see almost all of these at the AMS Hurricanes Conference for those who are going. Okay, and then, more present here. There's a bit of a common theme here. We all like food. Our research group talks about food quite a lot. And so, everyone, I think, here more or less knows everybody else, except perhaps Cameron and Zach, who are two pretty awesome undergrads at the time who we worked with a lot during COVID. On Zoom, and then together with Sam that we put a nice paper together as well. So the undergrad side of research is also pretty exciting. That a lot of them are really quite driven, and we do a lot of interesting work there too. Okay, right, onto like a key research result from each different person here, or each different project. So we'll just have a couple on track right now. So the question here is fairly basic, that in the bottom left-hand corner, we just have a very simplified version of the National Hurricane Center's cone of uncertainty that we all look at whenever a tropical cyclone is approaching. And that is based on the 67th percentile of forecasters' errors over the past 5 years. It does not change for different storms during the same year. So it's what one refers to as just a static cone of uncertainty. We thought back then, and Pete Finocchio was an undergrad at this time, we thought, well, why don't we use operational ensembles to see whether, if you've got a bigger spread of ensemble members, then you've probably got more uncertainty in the forecast. Let's try and bake that into a different cone. And then, on the contrary, if you have a storm that's got relatively high predictability and relatively low spread, then let's have a narrow cone. And so we took the ECMWF ensemble here. This is an example for Hurricane Ike, which struck Houston. And then we created 67th percentile circles to create these dynamic cones, and we evaluated them for hurricane season 2008. And actually, the dynamic cone did better than the static NHC cone for that year. It's a limited sample, and we moved on to other things. Now it's pretty interesting. Now we're in the mid-2020s. It's about 15 years since we did this study. And there have been some more advanced studies with ellipses of uncertainty since then. But now operational centers are finally coming around and thinking, oh yeah, we should do dynamic cones of uncertainty. So it's kind of nice to do work that has direct operational relevance. Speaking of which, and with the National Hurricane Center, around 2010, I collaborated quite a bit with Mike Brennan, who's now the director of the National Hurricane Center. But back then, he was a recently hired hurricane specialist who had a lot of interest and a pretty strong skill set in research. And Hurricane Ike, as you mentioned, was a pretty important hurricane. And so Mike said there was quite a lot of concern with some of the forecasts of Hurricane Ike, that the GFS forecast actually had Ike, which was just to the south of us at this initial time, just moving more or less sort of westward towards the Texas-Mexico border, which was not a great forecast. So Mike produced this map and then suggested, well, in the GFS, which I had access to then, I could assimilate synthetic observations in each of these chosen areas that were ridges or trough areas, and then run the GFS for each of these initial perturbations and see what the forecast did. And so we did that, and here are all the different tracks. So remember, the operational GFS was just kind of more or less straight line here, and then so are many of these, which say that perturbing some of these ridges and troughs made very little difference. But if we look at the green and the blue lines here, that those produce tracks that at least curved Ike a little bit more towards where Ike actually made landfall. And so those corresponded to a weakening of the ridge directly north of Ike, and also the strengthening of a little shortwave off California. And so if we had some better observations at that time, maybe sort of more concentrated observations, then perhaps the forecast might have been a little closer to reality. Yeah, Amy?
Just a quick question. Did you actually only put 4 sets of 4 points for constraining the operational constraints in?
Yeah.
Or is that just the area?
Yeah, so Amy's question was, did we just assimilate 4 data points in the GFS system? And yes, we did. So yeah, and then that of course included the entire global observational network with it. But I also created perfect observations, and I said, you will get through the quality control here. And I made some temperature perturbations that were quite large. So I did try and modify these ridges and troughs sort of somewhat dramatically, even with just 4 observations. So yeah, that was a fun and interesting study there. And then one of my first students, Monohiko Yamaguchi from Japan, he wanted to come and work with Dave Nolan and myself and really work in dynamics. He actually came from an operational center in Japan. And so he had worked a lot in ensemble forecasting as well. And so he wanted to see whether there are any dynamical explanations for how ensemble forecasts spread out. And so he looked at ECMWF ensembles, and he found, sort of much to our collective surprise, that baroclinic energy conversion in the vortex might be associated or explained in ensemble perturbations. So what we have here, these figures, are some classical theory that in your general circulation course and other courses, that one can think of like a North Pole right here, and then think about sort of temperature and stream function perturbations sort of going around the North Pole, so in the mid-latitudes. Here, Monohiko said, well, we've got a warm core tropical cyclone, and we have temperature and stream function perturbations around the cyclone, so 100 kilometers or so out from it. And so they sort of follow each other in this sort of pi by 4 phase difference right here. So this is purely from theory. And then the radial heat flux here, which is a U prime T prime at the bottom, then you've got these maxima at these particular regions around the azimuth. So then you looked at an ensemble member, and so these are the same plots, but with an ensemble member, and we see that they look somewhat similar. And so we see that he's plotted here the string function perturbations in the shading and the temperature perturbations in the contours, and it turned out that there's a fairly similar sort of picture pattern here of where the perturbation is drawing the eddy available potential energy from the mean flow. So it's interesting that he saw something that's baroclinic instability. Now he did further work with Dave Nolan on barotropic instability and found that too in some idealized models of tropical cyclones. So that was fun. That's all I'm going to talk about with track. So let's move on to Genesis here. Sorry, I just need to hide the zoom controls here. Okay. So this is another operationally motivated question, and it's driven by the National Hurricane Center's graph called Tropical Weather Outlooks that have the different colored blobs for the percentages of genesis. And so we worked on some field experiments here in the early 2010s, and I created these ensemble forecasts and then try to estimate the probability of genesis through them. So did this with Ryan Torn, and so Ryan and I came up with a metric for a tropical cyclone that uses the circulation, which is a low-level area average vorticity, and then a local thickness anomaly that then identifies perhaps where you've got a warm core in a forecast of a developing cyclone. And we set thresholds, and then when we had ensemble members that exceeded these thresholds, and we can make a probabilistic forecast for genesis. So we evaluated this over 3 seasons, and we sort of found some mixed results that sometimes we had some pretty good probabilistic predictions, but we couldn't really add much value, I think, at that time. I've come back to this 10 years later with ECMWF, and the results are quite promising, especially the last year. I think as ECMWF have gone to 9-kilometer ensembles too. But we have found difficulties with broad circulations, weak waves, and tropical transitions. And this sort of also opens up the question, which is a bit of a running theme in this Genesis section, that there's a lot of variability between cases, and there's not really a one-size-fits-all in the way that we understand or predict tropical cyclogenesis. And part of that study was also the former PhD student, Will Kamarami. And so Will asked a few questions also using ECMWF ensembles, including how predictable are these variables relevant to genesis and how are they related to each other. One conclusion was that with wind shear, that one could see that the wind shear forecast skill was better than climatology, even up to and beyond 10 days in some regimes. So a lot of this work sort of comes back to the Lorenz world, that conclusions can be very much based on the flow regime. And then this picture here with all these coloured blocks, it shows over the full 2010 season for all ECMWF ensemble members, just sort of binning the circulation and the shear values. And where the yellows are, that's where you've got the highest density of cases. And it's probably not surprising that where you've got the highest shear, the yellowest one here, that you've got lower circulations in your developing waves. However, we do see a lot of variability here, where you've even got low shear and low circulation, or high shear and stronger circulation. So there is a lot of variability here. This isn't just a very sort of focused joint probability density function here. Okay, moving on now to Quinton, and I'm sure that you all know Quinton, and you also know that he talks about convectively coupled Kelvin waves a lot. So you'll have seen his COMPASS seminar, and then also he'll be defending his PhD in April on a date that we're trying to figure out right now. And so his overarching question is, do convectively coupled Kelvin waves influence tropical cyclogenesis? And so this also brings a scale question into account here, that Kelvin waves are largely sort of synoptic to planetary scale waves. And so this is really a scale interaction between these very large scales and then even the convective scales, which are very important for genesis. And so in this animation here from Quinton, that we have this convectively active phase here in green and the convectively suppressed phase in brown. And we have here this sort of track of an African easterly wave using Quinton's tracker. And if we just look at it now, then we just see that the green part passes through and then genesis occurs just about a day or so later. This was a fairly insignificant storm from called Kirk, but it was really interesting for this case. But I won't steal Quinton's thunder anymore, that you can all come to his defense. Okay, still on the topic of genesis here, so here's Will Downes's work. So Will's a third-year PhD student sitting at the back. And so Will was very interested in studying rather unusual mechanisms of genesis, that those are ones that have the lower predictability. And so he wanted to build a tracker for it, because he had noticed that the conventional trackers were not really able to capture some of these weaker easterly waves or interacting easterly waves. And so he, together with Aidan, pulled out about 20 or so years of National Hurricane Center forecast discussions, which gave coordinates of African easterly waves and coordinates of the intertropical convergence zone. And then Will, through some magic, through AI, used these together with the RA5 and very carefully developed and evaluated whether one can use AI as a tool for identifying and predicting these really important tropical features. So here's an example with the ITCZ and the monsoon trough here. And then here are a couple of Hofmüller diagrams, which I'll go through a bit, that sort of show how his network predictions compare with other trackers. So we've got Quinton's tracker here from 2022, which was very much a state-of-the-art in 2022, and really sort of used some previous trackers and improved upon it. The time goes down from June to October here, and then the longitude goes from Africa all the way to the Eastern Pacific here on each of these three panels. And so each of these streaks shows African easterly waves that are propagating westwards. We see with more conventional trackers that it starts to fade out a bit beyond about 60 west or so. The middle tracker here by Margaret Hollis et al., it also sort of has a bit of a yellow zone in here too, that the waves tend to sort of get lost in the trackers, even though they exist in reality just as weak waves. The forecasters who write the discussions, that they track the waves subjectively through looking at convective clouds and so on. With Will, so you can see quite a lot of these streaks really go all the way into the Caribbean here. So this is showing quite a lot of promise, and the Hurricane Center is quite excited about this too. But Will's giving a Compass seminar, so you can all go to his and learn a lot more about it. Okay, another third-year student also sitting in the back is Alexis. And so Alexis is tackling a rather different genesis question here. And this sort of stems out of a NASA field experiment called CPEX that Alexis was involved in. And it involves a Caribbean low-level jet. Now, the low-level jet in the Caribbean is usually detrimental to genesis because it increases wind shear in that region. And there really hasn't been a lot of work done about the influence of the Caribbean low-level jet on tropical cyclones. Then there's this perfect poster child case which occurred during the experiment that became Hurricane Ida. But Ida took a pretty amazing confluence of factors to even develop at all. Now, unfortunately, it did. It made landfall as a Cat 4 in New Orleans and caused a lot of damage up in New York City, unfortunately, as well. And so what Alexis has here is a trough axis with 700 millibar winds. And so we see that there's some cyclonic vorticity here associated with a very weak African easterly wave. Then we go to the bottom figure here, and we see that there's some convection just on the east side of this trough axis. And then also where Alexis's arrow is pointing to is Venezuela. And there's actually some moist flow that's then producing some fairly copious precipitation that's induced by mountains over Venezuela. And this may have had a really substantial influence, together with this convection, in helping to amplify the wave and develop it into a tropical cyclone. So this is a rather unusual and interesting genesis mechanism, and Alexis is really looking into how those mechanisms, if there are other cases that sort of follow these types of mechanisms. And then finally, on the topic of genesis and really leading in tropical cyclone activity, that Ben Kerman and I had an awesome grad student called Kurt Hansen, who a few of you know. And Kurt was very interested in sub-seasonal prediction. So that's the time scales of sort of 2 to 6 weeks. So we can't really look at individual storms there, but then also this should be a bit more sophisticated than just the influences of El Nino, for example. So what Kurt did was he filtered out weather signals and he filtered out seasonal signals and then tried to make some sense out of what's left. And they're really not very clear signals on the sub-seasonal scales. What he did find in his first paper from the reanalysis data was there's this kind of dipole of shear anomaly that you get anomalously high tropical cyclone activity on sub-seasonal scales if you've got a high shear anomaly here east of us and you've got a low shear anomaly in the Caribbean. And the sources of these may be the Mann-Julian oscillation or mid-latitude influence potential vorticity streamers. So he's hypothesized those. He just had a 2024 paper just accepted in GRL literally 2 days ago, so that's all very exciting too. So this was a nice sort of trio of studies right here, and he's now evaluating this in Navy models for his postdoc. Okay, we will move to intensity change. I'm not sure I'll get around to data assimilation, but that's okay. We'll look at the intensity change part. And so this is the work of Pete Finocchio. And so Pete asked some pretty fundamental questions about how predictability may be influenced by little changes to the vertical wind shear profile. And so for all of his studies, he used Dave Nolan's point downscaling framework using the Whorf model. And so based on observations, Pete created these vertical profiles of wind here. So there's a little variability in these wind profiles. They created a 20-member ensemble and then assessed the difference across these different ensemble members. And I'm not showing it here, but he sort of quantified predictability out of that. A key point here, just to say, is that these ensemble members look quite different after about 3 days, even though these deep shear profiles look to the naked eye as sort of fairly similar. He also perturbed the shallow upper level shear and found not so much variability in these. And then following Pete was Yi Dai, and so Yi was also an Office of Naval Research grant, and that was all about outflow. And so Yi, together with Dave and myself, it's actually pretty amazing what Yi did. He used one simulation. He got 3 papers out of it. And that simulation essentially had like a good chunk of a hurricane life cycle that involved a rain band formation, a secondary eye wall formation, and a tropical cyclone that was experiencing fairly strong shear. In this particular slide here, all I'm showing is an example where you have a tropical cyclone, but you've got some fairly asymmetric convection to the north. And off the map here is a zonal jet. And so in Dave's modeling framework, you put a jet in, put a cyclone in, and then study the role of the outflow in influencing this rain band. And so in this jet simulation, which is on the top here, this is a cross-section that's down shear left, and it's going from southeast to northwest. And if we look at the northwestern side here, then we see that actually this is at the level of the jet, that we have outflow right here, and then these black contours are updrafts. And so the outflow is inducing this upward motion here, which is starting the formation of the eye wall, and then there's a return flow, so there's kind of secondary circulation in the hurricane here that's being, or well, tropical storm at this stage, it's being induced. So this is all some quite interesting hypothesis-driven work using idealized modeling. Okay, following Yi, there was Sam. And so this is on now focusing more on rapid intensification and whether one can discriminate between rapid and slower intensification with different wind shear and humidity profiles. So I also won't steal Sam's thunder, as she's giving a COMPASS talk in early March, and you can all come to that. Sam published a paper a few months ago that's a statistical examination of whether the probability density functions for shear and other variables look different for rapidly intensifying cases versus more slowly intensifying cases. And so we do see that the blues stand out for lower shear, and so one can say that one can discriminate between the different intensification rates and shear. But there is a lot of overlap between them, especially if you look at 15 knots of shear, that's a little kind of ambiguous about what a more likely intensification rate is. That all of this is to say that there are so many other variables that one needs to look at in conjunction to really try and make statistical predictions of intensity change and rapid intensification. Moisture was not really very clear statistically, but Sam did find something very interesting for some cases. And here's one for Hurricane Dorian from 2019, where this is the shear vector, and it's in the up shear right quadrant that there's this influx of moisture that actually was a very key factor in Dorian's onset of rapid intensification. And so the up shear right quadrant hasn't been studied that much in the literature. So that was really interesting. And so Sam's now working a lot on idealized WRF modeling to sort of study these from a more sort of process-based perspective, and is having a lot of fun with that right now. Okay, and then some of my work on intensity change when I was on sabbatical at ECMWF was I was a kid in a candy store. The ECMWF had this 4-kilometer in-house global model, and so we wanted to see whether it could capture realistic tropical cyclone structures. It could to a certain extent. That this is a very cherry-picked case here for Hurricane Laura in 2020, and EC4 is a 4-kilometer ECMWF. EC9 is the operational ECMWF. So we see in our vertical cross-sections of total wind, it's a much weaker tropical cyclone than what was actually a Cat 4 at this time. This is the 4-kilometer COAMS model that the Navy runs, which can simulate very intense hurricanes. It just happens to have a slightly weaker forecast here. And then for secondary circulations, we have inflow that was stronger in a 4-kilometer ECMWF than 9-kilometer. And then also a much deeper warm core that represented here in the temperature anomaly. However, there were some real challenges with the ECMWF, especially for rapid intensification, but COAMS had those as well. But with ECMWF, with the operational data assimilation, it just does not have the resolution to capture eye walls and the winds in eye walls realistically. And so there's always this sort of slow spin up that any sort of forward model has to do from this sort of rather usually biased weak tropical cyclone. So that moves us to data assimilation, which I'll go through just a little bit quickly here, so I don't want to leave a couple of my other students out. So this is from Ting-Chi Wu, who graduated 10 years ago with a PhD. And this was a project that was driven a lot by the University of Wisconsin, who are the people who create the atmospheric motion vectors, and one looks at their website quite a lot during hurricane season. And so she was one of the first to try and assimilate these in mesoscale models in research mode. And now this is done operationally, but this is one of the first studies, and it gets cited quite a lot because of it, which is quite nice. And so she found that these atmospheric motion vectors, especially in the interior and also upper layers, that they tended to make the most improvement to the structure. I won't really go much more into it except to say that this was really interesting work that had to combine a lot of different fields. Data assimilation is in a world in itself, then there's satellite meteorology, and then there's tropical cyclones. Here's one direct contribution to operations that we did at ECMWF, that we ran about 15 different data assimilation experiments over the 2020 season. And one of those was that we doubled the amount of scatterometer data compared with what's assimilated operationally. And this again is a very cherry-picked case for Typhoon Maisak in 2020, which is quite an intense typhoon. And this doubling the amount of scatterometer data produced a more intense typhoon, which was good. So now, operationally, ECMWF doubled the scatterometer data and then adjusted, inflated their observation errors accordingly for that. So that was a nice little operational transition as part of our research. We also work on the Cygnus satellite, which is a low latitude orbiting satellite with many different revisits through the day compared with scatterometers. And also, since it's based on reflected GPS signals, it can see through convection. So here's an example produced by Brian McNulty that shows the type of coverage that one gets in a hurricane. But a lot of the work is still under development here in its potential for improving hurricane forecasting. And then last but not least, and this is really looking to the future, is Lisa Bucci's PhD that she graduated in 2020. And so she's very interested in Doppler wind lidars, both on aircraft and on satellites. And so this is trying to inform NASA of the future potential for Doppler wind lidars to improve analyses and forecasts. So this uses a tool called Observing System Simulation Experiments. And with the Hurricane Research Division, this was really led by Bob Atlas, a former AOML director. This OSSI framework was set up by Lisa and others. And one of the others is Dave Nolan, that he developed this regional nature run that's really heavily cited and award-winning. And the purpose of nature run is that that's your truth. That in an OSSI, you really work in this total fantasy world where you have a realistic weather system, whatever weather system is, and then you sample synthetic observations out of that truth with appropriate errors. And then you take an operational quality model and data assimilation scheme and you test the impact of observations such as these LiDAR observations. So I'm going to stop there. This is just the final slide on some future directions here. So the first part is a little bit sort of more of the same in a way, but a lot of interest in looking at regime dependence, and particularly this sort of genesis to early intensification, and that's sort of relatively unexplored. Yeah, everyone likes a cat fires. I find cat fires boring. A lot of work's been done on Genesis, and that's still very interesting, but it's just after Genesis, it's still very disorganized and asymmetric. But some of those storms intensify rapidly, others don't, and so that's a big area of interest. Also following Kurt's works on the predictability and extended timescales, and also building some climatology work that I haven't discussed much here, but recently published, is interesting. Also, evaluation, I actually find that an interesting area of science, but it hasn't really been done too much, but I have a lot of ideas about that. And also just taking AI models and doing some more physically based evaluations to see whether, are they just getting great statistics, or are they actually producing realistic, physically realistic figures. And then I have another project with Brian McNulty and collaborators on our main campus and at NCAR on hazard risk communication. That's a really sort of burgeoning area of research right now as well. So I'm going to stop there and apologize for going quite long there. I think I did my 30 papers in 30 slides, just. So if there's time for questions, then I'll be glad to take any. Cam?
Yeah, awesome. That was really great. My question is, with your work with the ECMWF, if you've had a chance to do a preliminary analysis of the machine learning models, and if you have direct work with that. And then I had another research question with your paper with Dr. Nolan and Dr. Finocchio. Do you think that the alignment process in the TCs with a deeper layer of shear was more caused by the tilt being in the up shear quadrant versus down shear, or the magnitude of the tilt in kilometers or so?
Yeah, okay. Yeah, two very good questions there. So the first question about ECMWF machine learning models, they've just come online, and they've shown some pretty substantial improvements compared with their sort of very long developed operational system. And I haven't started evaluating those yet, but I'd like to in the near future, sort of more sort of process-based. And the second question about Pete Finocchio's PhD research on the sort of predictability of tropical cyclone intensity change on the different prescriptions of shear, that with the deep shear, that really where it changes, really, you got the answer right, was that it's really changes in the tilt. And I forget the exact sort of type of tilt, whether it's up shear or not. But that's where there was this real variability, was just that some members really tilted one way, other members had a very different tilt, and that really caused a large variability in the solutions. But yeah, your point was right on, that it was a tilt that was the main sort of factor in that, sort of driven by small changes in the shear. Amy.
Thanks. I realized how much, we talked to each other and I didn't know any of this, so thank you for sharing and putting it all together. It's been nice. You mentioned it in a couple instances, this kind of easy transition between, we got this result, and then they started operationalizing it. And I'm sure that there's like things that work and things that don't in that process.
Yeah,
Can you talk
so
a
this,
bit more about that?
Yeah, this is a really interesting, important, and sometimes controversial point about research and its transition into operations. And so that can be quite hit or miss. It's really whether there's an operational adopter that's excited by it. And Quentin and I were actually just discussing this a little bit this morning, is with agencies such as ECMWF and the US Navy, that they have research and operations on the same site. And so there's a very sort of seamless transition, because there's not really a distinction between the two. And so they see the scalerometer result, they see the proof of concept and some statistical significance, they say, okay, we'll do it. With some agencies, such as NOAA, they're getting better at that, but that's been a little bit of a challenge through the years. But they do have a good sort of formal transition process to operations. It's just that there, the research and the operations can sometimes be a little bit more distinct. So like the dynamic cones, that's like about 15 years later, after Pete and I had published, and a few others, Tom Hamlin and others had published, that with them it's typically about a 10+ year process. Now, there's also taking things out of operations. I actually helped stop the winter storm reconnaissance program. I'm just like, why is this continuing? I'm angry as a taxpayer about it. No one's doing any evaluations of this program at all. So ECMWF were like, well, we're going to do it, and then it showed absolutely no impact at all. And so they took that program down after 15 years. And I'm like, good. They actually brought it back more recently, and that's fine. So they want to sample one convention scale. Jonathan.
Yeah, I was going to ask, so do you have any theories as to why the experimental products produce different results from the operational?
So Jonathan's question was about whether we have any thoughts about why the experimental products are different from the operational products. In which particular context?
I think it was when you were talking about the EC.
Yeah. Oh yeah, so that's a 4 kilometer versus a 9 kilometer there. And so the 4 kilometer, the advantage of that is that it's better able to, once it's spun up, it's better able to create eye walls in the hurricane, and so it's just better able to resolve processes that are on the convective scale, although the convection was still parameterized there. So it's just able to resolve finer scale features. I'll probably leave it at that because there's a lots of underneath the hood that is a little confusing even to all of us at ECMWF.
Next question was interesting graph showing dependence of hurricane intensity on shear somewhere at the beginning. So that's probably related to El Nino cycles because strong shear, low shear, depending what is the phase. And then it was a kind of intermediate or maybe low shear when we saw maximum intensification, rapid intensification. Then does it go well along with predictions of Dr. Gray years ago, seasonal predictions?
So yeah, your question, I think it's more related to Kurt Hansen's research on the subseasonal scales. And what he did was he removed the signals from seasonal oscillations such as ENSO. And so it strictly looks at the subseasonal variability. So that involves more features such as the Madden-Julian oscillation. That popped up quite strongly in his statistical signals, which I didn't show. But yeah, you're right that Dr. Gray and other predictions, that they do more seasonal predictions, and so they correctly include the influence of ENSO, and that can override influences that are subseasonal. And subseasonal signals are a little bit more subtle, but yeah, he was just very interested in that subseasonal range.
Thank you.
Are there any questions online,
Yeah, someone asked, did the Cohen's model use ECMWF operational for ICs and DC for the comparison you presented for the RI case?
Okay, yeah, thanks for the question there, Frank. Yeah, and that's an important point. The Cohens use their own initialization, which is a synthetic vortex that they essentially create what's called a Rankine vortex, just based on the operational parameters. So they do that for tropical storms with at least 55 knot intensity. So yeah, it's comparing apples and oranges a little bit because the model physics are also quite different as well as the initial conditions. And yeah, that was a struggle with the reviewers too. Yeah, good question.
Well, thanks everyone for coming. Thank you, Sharan.
Thank you for staying.